as I say, it's the last of the 15-minute talk, so hopefully everyone can stay awake just a little bit longer before we head out for our dinner. So yeah, I'm Sophie, and this is some work that I'm doing as part of my PhD, trying to prove estimates of centre of mass. And I'll start off just by giving you a bit of background of what people have done so far on this topic, just to kick off. So, centre of mass, what is it? The dictionary definition is it's the point at which you can think of all of the mass being concentrated in an object. So it's quite simple if it's a straightforward 2D shape. It's important in organisms because an organism needs to make sure that its centre of mass stays between the area of support that it's got defined by its limbs. If it's not, then you will fall over, like this guy. Admittedly, there's been some foul play there, but same principle applies, okay? And if you know an organism's centre of mass, you can tell what its posture is when it's stood still or when it's moving, and you can eliminate postures that are impossible and really get a better idea about that. And obviously, in fossils, that sort of information is invaluable, that indirect route to information about how it stood, how it moved. When you can't observe it directly, that's really important. So, needless to say, people are very interested in doing this. But unfortunately, centre of mass is quite difficult to estimate. The best method depends very much on what you're studying. Do you want to hang it off a string, as Alexander's doing up there? That's difficult if it's a full-size elephant, obviously. Is it alive? Is it a model that you've made? Is it cadaveric? Is it living and breathing? Is it a fossil? Nothing is straightforward, regardless of which of those you're choosing. The digital modelling, as in many fields, has sort of emerged as the best method that we can use. It's got a lot of advantages. And one of the best here is that you can apply the same method to your alligator in this case and to your T-Rex and really quantify the error and the uncertainty that's in your method, in your extant thing, and then apply that to the fossil. So that's the approach that we're using moving forward. And people have done that in the past, but it is difficult to estimate centre of mass. There's a lot of input data that you require, and actually that's not really available in many cases. So people have had to estimate soft tissue volumes, but there isn't really information on how that works in living things. And so there have been subjective estimates basically drawing around skeletons to make something that vaguely looks like a T-Rex, which isn't ideal. People have included air cavities, which is fine. That's based on a fossil record. Again, it's not really grounded in anything that we know about living animals. And the density data that's used is, again, based on not a lot of data. There's room for improvement, and I've left my lovely figures out here. This is just to show you the extremes of skin outlines that people end up having to use. The minimum version there looks completely emaciated. It's ridiculous, but equally the maximum is insane as well. That's an obese T-Rex, which is insane. Here's some nice air cavities that someone's put into an Archaeopteryx model, but again, it's a bit of a question mark as to how accurate they are. And yeah, the density data people have collected using various iterations of Archimedes' principle, but it's not a cohesive data set by any stretch of the imagination. So there's room for improvement here, and that's what we're looking to do, to really improve this input data, and hopefully at the end of the day that will help us make better models, or at least we can understand better the variation that's present and recognise that maybe we just don't know these things about fossils. So just to give you a nice equation to soak up that seems to have gone crazy on a map, which is nice. Guess what that used to say. Basically, to work out centre of mass, you want to add up the masses of all your individual segments, and there's a weighting given to that based on how far it is from the centre of the organism. A heavy hand on the end of your limb is going to have more effect than if it was closer to the body itself. But again, all these parameters, you need input data to put in to generate the data. So for each component that you want to consider, you need the volume and the density, and this is what's going to keep coming back up. Organisms are complicated. They're not a simple cube. They're 3D. They've got complex geometries. and that just makes it even more complicated. That's just biology for you. In my final piece of work, we will end up considering 3 main components, so soft tissue, which is obviously the bulk of an organism, the air cavities, which are taking away some of the mass, and the integument, which is actually something that hasn't really been looked at before. I'm not going to address air cavities here because there isn't time, it's not really my area of expertise, but we'll start off with soft tissue. So obviously it's quite easy in extant things. Got an alligator here, you can see his skeleton sort of showing through his skin, and you can see the relationship between its skeleton and his skin and the different ratios in the different parts of the body. So that's really straightforward, and we want to really tap into this information in the living things. So taking sort of an extant phylogenetic bracket, that's an iguana and an alligator and a parrot, to learn about the ratios between skeletal volume and skin volume in the extinct critters that we're interested in, the dinosaurs. I've got some preliminary data which is sort of showing us some quite nice trends. This is for the shank segment. Got a lot of bird data, I need to fill in some more crop and lizardy things, but it's looking fairly nice apart from on one anomaly. Not quite sure what that is or why that's generated it, but it's quite nice. It's quite a nice relationship, it's promising. Some segments are more variable. So this is the femur segment. And you would expect it to be more variable, and I would envisage that that's going to continue to happen across all the segments just because of the variation that is present. And birds in particular, like femurs are funky, the flesh around them. And we're going to look at improving our density data that we input into these models as well. And the hope is that if we can really nail this soft tissue element and really quantify the relationship between skeletal volume and skin volume, then we can predict this much better in the extinct animals. If we can do that well for the soft tissue, then that's the bulk of the organism sorted, and the rest of it is just the icing on the cake. Move on to another component. As I say, this has never been considered before. No one has ever added, as far as I'm aware, integument to models of archosaur centre of mass. Which you might think, well, yeah, but feathers, light as a feather, they don't weigh much, right? Well, actually, yeah, they can do. Up to 14% of a bird's body mass, which is quite substantial. But nobody knows what effect that they might have on centre of mass position. When you think about the fact that they're going to be distributed mainly on the wings, actually it could have significant impacts. So we've collected some data on a load of feathers from a whole host of birds. This is a nice chunk of an ostrich. Apologies if anyone's slightly squeamish. And basically worked out the density by taking chunks like this, working out surface area, taking the mass, etc., etc. And we're going to be able to apply these to our models. We've got data for flight feathers, for the general body feathers, and for scales as well. So that's the plan. I've got some preliminary results for this, just in terms of not applying it to the models, but just what are feathers' mass properties, because nobody's looked at it, and it comes out with some fairly interesting results, I thought. This first one, so general feathers, there's no difference in density between any of the different regions that we looked at, which makes our lives easier when it comes to the modelling. Maybe not that surprising. The flight feathers are much more interesting. The density of the different types of flight feather did differ between the regions. So your primary and your caudal flight feathers formed one sort of distinct group, and then the secondary and tertiary flight feathers are much less dense. And also significant differences between the surface area of different flight feathers, according to the locomotor type of the birds that we were looking at, which isn't surprising, but it's nice to have that quantified and have that actually demonstrated. And there was some funky stuff going on with the scales as well, so significant differences in the density, depending on whether it was a lizard, a crocodilian, or a bird, which is quite interesting and something to explore further. And once we've generated all of this lovely data, it's no good just to plug it into a model and say, well, that's a model with the most data in it that a model has ever had, and therefore it must be brilliant because we've made it. You can't say that, you can't assume that. You need to validate it. You need to physically validate it, so hang it off a string, essentially, suspension methods on your on your actual specimen that you physically got, your bird or your crop or whatever, and then build a model and compare the two answers that you get and see how close you are actually getting. Hopefully you're reasonably close, but you never know, and actually that is valuable information when you then want to go on and apply it to fossils, when you're already having to make all sorts of assumptions anyway. You need to know what uncertainty is inherent in your method, otherwise you're just blowing smoke. So that's the plan. And just a quick sort of like look forward, what are we hoping to achieve with all this once we've come up with this hopefully super method that will make awesome models. Couple of things. I'm going to apply it to some representatives of living birds to try and really understand their evolution and their ecology, because they're such a diverse group, but not much is understood about them at the moment and how those factors have evolved. So that will be interesting. And also to fossil taxa as well. I can't see adding 15% worth of feathers to T-Rex is going to make a massive difference, but you never know, could do. But particularly interesting will be to see what kind of effects it has on sort of the organisms that are making the transition to continuous flight, who've got contested flight capabilities, and just to see, does this shift centre of mass to such an extent that actually it can shed new light for us on the behaviours of these critters in combination with everything that's been done before. So, and if anyone else has got any ideas about exciting species that we could look at and questions that we could ask the teams, then I'd love to hear them. And all that's left to say is thanks to all this lot. I will plug our blog because I've been asked to. It's new. We have a Twitter page if you're interested in hearing about biomechanical research, stuff like this. Please check it out. Thank you guys for listening. If anyone's got any questions, then I'd be happy to hear them.